Okay. The good morning to all. Welcome for this the fourth session of this ATD. Now, in the previous class, we are all discussed about this diesel cycle. Before that, the Carnot cycle, Otto cycle. From there, you find that it's the thermal efficiency of the Otto cycle, and then in the yesterday's class, we found that the thermal efficiency of the diesel cycle, and then mean effective pressure. After that, the different cycles and different process, and then how they are working, all the things we are all the familiar with that the diesel cycle, and then we are further on to this the problems on diesel cycle. The in the examination he is asking lot of times this the problems on diesel cycle, so that at the time of doing the diesel cycle only I am solving this few numericals, because the after the derivation you are very much familiar about the transformation of the different formulas in the diesel cycle, so that it is very easy to solve, and then you are more familiar with the different formulas in the diesel cycle, so that you are feeling a little bit comfortable in the diesel cycle problems. Before that, okay, here is one problem is there. We'll take this. One problem. The pressure on the compression curve of the diesel cycle are given as 14 bar at 1/8 of the stroke and 1.4 bar at 7 by 8 of the stroke. Determine the compression ratio, air standard efficiency, and the mean effective pressure of the cutoff occurs at 1/6 of the stroke. Assume the pressure and temperature at the beginning of the adiabatic compression is 1.1 bar and 27 degree respectively. Given data are like this. Diesel cycle PA. Here you see here 1 to 2 is the compression process. 3 to 4 is the expansion process. 2 to 3 is constant pressure heat addition. 4 to 1 is constant volume heat rejection, as you all know that. But here he is mentioning the pressure on the compression curve. Compression curve is this one, 1 to 2 compression process. Pressure on the compression curve of the diesel engine are given 14 bar after 1/8 of the stroke. If you divide this 1 to 2 into 8 parts, after the one part, the past, well, after the part of the compression stroke, the pressure is 114 bar. That is denoted by A. Here is PA is 14 bar, and then stroke 1.4 after 7/8. From here 1 to 2, if you divide that into 8 parts, after the 8 part, 7 parts are over, remaining is only one part. That is 1 by 8. Okay, like that you must divide this. Determine the compression ratio R suffix C and air standard efficiency and mean effective pressure of the cutoff occurs at 1 by 16th of the stroke. Here 3 is 1 by 16th of Vs. Stroke is Vs. See, assume the air that CP, R and gamma. These are things you must assume it. To calculate the cutoff ratio, air standard efficiency, mean effective pressure. For this, you see here, for isentropic process, PA by PB. PA by PB is VB by VA raised to the power of gamma, right? Raised to the power of gamma. If you go to the previous one, here PA by PB, 1 by 8 and 7 by 8 of this 1 to 2, 7 by 8 of this 1 to 2, right? V2 plus VA is V2 plus 1 by 8 of Vs V2 plus 7 by 8 of Vs. How? This is Vs now. From here, the Va is 1 by 8 of Vs. V2 is this one. V2 plus this from 0. Okay? V2 plus 7 by 8. VB by VA. Right? From here, the PA is 1.4 by 14. You'll get this equation. And then thermal efficiency is this. After that, if you calculate the R, the compression ratio and all those things, you'll get the mean effective pressure and the thermal efficiency. I'll move on to the second this thing. Diesel cycle has a compression ratio is 14 and the compression and the cutoff ratio is 2.2 rho and CP. The RC, this one is calculate the standard efficiency and pressure and temperature of all the salient points, assuming that the pressure and temperature at the beginning of the cycle is 0.98 bar. Okay, 98 bar. Here, first thing what you have to do, you have to write the the PV and ES diagram. This carries 2 marks. After that, you write the given data, and then these are the assumptions needed to calculate the air standard efficiency and pressure and temperature of all the cells. Thermal efficiency you can calculate by using the R is 1.4, gamma is 1.4, and R is 14. Cutoff ratio 2.2 is given. If you calculate directly, you'll get the because the compression ratio also is given, cutoff ratio also is given, and gamma also is given. Okay, for the process 1 to 2, P2 by P1, V1 by V2 raised to the power of gamma 1, RC to the power of gamma, it becomes P2, P1 into, you substitute all the things. P1 is 0.98 into 10 to the power of 5 into RC is 14, 1.4, you get the P2. T2 also same thing. Okay. In the process, after this, 2 to 3 is the ISO baric or the, I'm sorry, constant pressure heat supply process. P3 is equal to P2. This is the, if you come to this diagram, 2 and 3, the pressure is same. So that it is the P2 is equal to P3. P2 is equal to P3. P3 by V2 is equal to V2 by V1. From this equation, you'll get the T3 is 2358.28, this thing, Kelvin. V3 by V2 is gamma, that is yes given. And then RC is equal to V4 by V3, RC by rho, 1.14 by 2.2, it becomes the R expansion, reversible adiabatic expansion process, 6.36, RE. In the similar manner, you can calculate the P4. P4 is this one, P4 and T4 by using reversible adiabatic equation. Okay, like this T1, T2, T4, T5, all the things you are calculated. Now, very important one more cycle, that is the dual cycle. Dual cycle. It is also called as a limited pressure cycle, semi-diesel cycle, mixed cycle. In early compression ignition engines, fuel was injected when the piston reaches the top dead center. In the diesel engine, fuel was injected at the top dead center. Combustion lasted well in expansion stroke. The air standard cycle, air standard diesel cycle thus does not stimulate exactly the pressure and volume variation in the actual modern complex ignition engine. The modern engine, the fuel is injected before the top dead center, about 15 degrees earlier the top dead center. Dual combustion cycle is a closer approximation to the modern compression ignition engines, in which some part of the heat is added to the air at constant volume and remainder at the constant pressure. The only the thing is the summary of this is nothing but in some of the cases compression ignition engine it is not possible to supply the heat continuously at the constant pressure, but some of the heat is supplied in the constant pressure and some of the heat is supplied in the constant volume. That's why it is called as a dual or limited pressure cycle or semi-diesel cycle or mixed cycle, maybe any name you may call. See, here the PV diagram and temperature versus entropy diagram is like this. Here in the diesel cycle and Otto cycle, there are four process, but in case of dual cycle, we'll be having the 5 cycles. That is 1 to 2, 2 to 3, then 3 to 4, 4 to 5, 4 to 1. Let us discuss what are these processes. 1 to 2 is the isentropic or reversible adiabatic, because 1 to 2 it is the same, and 3, 4 to 5 is also same. And 2 to 3 is V is equal to constant. 3 to 4, P is equal to constant, means the pressure is constant and volume is constant. Some part of the heat is supplied. 2 to 3 is the constant pressure, constant volume. Some part of the heat is supplied at the 3 to 4, it is called as constant volume. Here equation used is Q is equal to MCP delta T is T3 minus T2. Here MCV T3 minus T2, MCP T4 minus T3, higher temperature minus lower temperature. 1 to 2 is the reversible adiabatic compression. Compression takes place here in this process. There is a compression ratio will come into picture with the V1 by V2, because V1 is from the intersection of axis. If you read this volume of the cylinder, 0 to 1 is the higher volume. That's why V1 by V2. The compression takes place between the 1 to 2 ends. The temperature increases to T2 and pressure increases to P2, volume decreases to V2. Like this, the entities are going to, or the some of the parameters are going to change. Isochoric constant volume heat supply. The constant volume heat supply is 2 to 3. MCV. CV is 7.18, constant value. For the problem solving sake, you need this, you must remember. Okay? And then at the end of the isentropic compression, heat is added to at the constant volume. The increase the pressure and temperature of the air. Here isobaric or constant pressure heat supply, isentropic reversible expansion, and isochoric heat rejection. Isentropic heat rejection. Here isochoric means constant volume heat rejection. It is a 4 to 5 is a reversible adiabatic expansion. Okay. Thermodynamic analysis is the same as diesel cycle and Otto cycle, but only the thing is here the heat supply is twice. Some part of the heat is supplied in the constant volume and some part of the heat is supplied in the constant 2 to 3, 2 to 4, 2 to 3, 3 to 4, both heat supply takes place. Heat supply starts from here and cutoff takes place here. The heat supply MCV T3 minus T2 plus MCP T4 minus T3. Heat rejected is MCV T5 minus T1. Okay, only one heat rejection. The efficiency is 1 minus Q out divided by Q in, 1 minus MCV T5 minus T1. Only one heat rejection is there. Two heat supplies at constant volume and constant pressure. After simplification, you will get the 1 minus T5 minus T1 divided by T3 minus T2 plus gamma T4 minus T3. like this, the thermal efficiency is there. Yeah, if you want to simplify the thermal efficiency of this, the dual cycle or limited pressure cycle, mixed pressure cycle, uh, these are the ratios are very much essential. The compression ratio occurs in the compression process. Cutoff ratio occurs in the fuel supply process. The expansion ratio, and then R suffix C is equal to compression ratio is equal to expansion ratio into the rho cutoff ratio. Explosion ratio, one more explosion ratio is there. The alpha P3 by P2. P3 by P2 is nothing but the constant volume it's applied. Here in the Otto cycle, there is a only compression ratio. Diesel cycle, there is a compression ratio, expansion ratio, and cutoff ratio. Third, in the dual cycle, there are four process ratios. One is cutoff ratio and compression ratio, expansion ratio, or explosion ratio. Four ratios. Okay, four ratios. Okay, today I'll stop here because little bit disturbance has happened. Let us discuss the few important things.